So let's find the Laplace transform for sine of 2t. So here, applying the definition again, take the integral of sine of 2t e to the minus st dt. We're going to do the integration of parts. In fact, we're not going to do it twice. So here we define again du. We define this to be v. So here we have v is equal to sine of 2t, and dv is just equal to 2 cosine of 2t. U is equal to e to the minus st dt, and that's du. And then we have u equal to negative 1 over s e to the minus st. So here our integration by parts is v du equals uv minus u dv integral. So using this set of expressions and substituted into our integration by parts equation, we have the following: the integral of v du is equal to sine of 2t, and du is e to the minus st dt is equal to uv negative 1 over s e to the minus st times v, which is sine of 2t, where we integrate this from 0 to infinity, minus u, going from 0 to infinity, negative 1 over s e to the minus st, that's our u, and then dv is 2 cosine of 2t dt. Alright, we note in this expression here that substituting for infinity, this expression goes to 0. Substituting the low limit of 0, sine of 2t equals 0. So this goes to 0, and we can rewrite this expression as equal to negative 2 over s integral from 0 to infinity cosine of 2t multiplied by e to the minus st dt. We're going to have to do the integration by parts again. Here we define this as du, and here we define as v. So with v equal to cosine of 2t, that implies dv is equal to negative 2 sine 2t dt. We have du equal to e to the minus st dt, therefore u is equal to negative 1 over s e to the minus st dt. Now we substitute this expression into our integration by parts expression, where we have v du is equal to uv minus u dv. Hence we have the expression of minus 2 over s cosine of 2t e to the minus st dt is equal to negative 2 over s. All that is going to be multiplied by u times v. So we have again negative 1 over s for u, e to the minus st. Oops, and I forgot this is not a dt here. So what we have, that's our u expression, and then v is cosine of 2t, going from 0 to infinity, minus, again we're going to have this, put a curly brackets here because we got our second expression or integral right here, going from 0 to infinity. U again is minus 1 over s e to the minus st times dv, which is just minus 2 sine 2t dt. Well, let's look at this expression here. When we substitute infinity, this limit goes to 0, the upper limit, and then the lower limit is just the minus, and the minus here cancels out, so that's a plus 2 over s squared. And then here, minus 2s multiplies by this negative 1 over s, so that's a positive 2s, but we still have a minus sign, so that's just minus 4, because we got the 2 here and a 2 here, over s squared. When we factor out this 1 over s, not factor it out, but leave it by itself, minus st sine of 2t dt, this expression is just simply the Laplace transform of sine of 2t by definition. All this is equal to the Laplace transform of sine of 2t. Alright? Putting the Laplace transform in the other side for this expression right here, we'll factor out the Laplace transform of sine of 2t. This expression is factored out, so we have one of those plus 4 over s squared is equal to 2 over s squared. So let's finish up this example where we want to multiply on both sides of this expression by s squared, and when we do that, we have the Laplace transform sine of 2t. We're going to multiply this by s squared, so this leaves s squared for this first term here, plus 4. And on the right side, we multiply by s squared, that leaves 2. Solving for sine of 2t then yields the following, which is equal to 2 over s squared plus 4. So that's our result for finding the Laplace transform of sine of 2t. I'll show you another way of finding it, but that can be found in a later video.